So yes, it's true, I'm another guy from Simula. I've prepared a down and dirty fight between the Dragonfly and the factory using very clean theoretical methods. So there won't be any splash on any of you. It's done together with a couple of guys from Simula, and also some people from Mellanox, including someone who's present here today. So I'll go through motivation for the work that's performed, the method we've used to do the comparison. I'll present the factory topology, which has lived for quite a long time, so most of you perhaps is familiar with it. I'll go into a bit more details on the Dragonfly than Pedro did. And then I'll dive into the comparison itself and try to draw some conclusions on the subject. So why do you want to do this comparison? The factory is the one big topology everyone is using in high performance computing now. It's been for some while. It's because it's very clearly defined. It's easy to build. People have built it for a long time. It's very easy to route, which is one of the points that were made earlier today. It has clear, predictable performance. You have full bisection bandwidth over the entire topology. You can more or less put any traffic pattern on it and expect pretty good performance. Downsides is that it's a bit difficult to scale. So within the range that's afforded by the exact switch size you've used and the number of layers you've used, you can have some kind of scalability. But as soon as you reach the limit, you have to add another layer, or you have to add switch all your switches to larger systems, which is terribly expensive. So along comes the Dragonfly to try to solve some of these problems. And one of the major motivations for the Dragonfly, I think, is that you don't really always need the totally non-blocking topology. It's expensive, and most of the time it's just wasted. So they're trying to make it a bit more efficient, reduce the number of global links. So they have they try to exploit the fact that electrical links are cheap, but they can't be too long, and optical links can have any length you want, more or less, but they're much more expensive. So they try to optimize on the optical links of the topology by reducing the overall bandwidth of the network without affecting performance too much. Trouble is, there's not been too much work presented on the Dragonfly. You have the two major papers from Kim with his compatriots. They present the basics of the topology and go into weird ways of performing adaptive routing in the topology to be able to perform to achieve the performance required for the system. I haven't gone too much into the theoretical details which we're used to knowing for all the topologies we work with. So for the mesh, you know the bisection bandwidth, you know how all the different properties change when you modify the parameters. Same for the torus and the factory. But for the Dragonfly, it's more of a bit of a black box. It just works with if you have a decent adaptive routing algorithm, apparently. And I also do a comparison with the factory, which is not too detailed, and it's a bit difficult to understand. You don't get all the assumptions they have in the comparison. So we try to do this again. And this time I trust it much more because I know all the details. I'll try to tell you some of the details, so perhaps you also believe some of my conclusions. And then we'll compare them and try to see how they behave and in which cases one would be better than the other. So this is one of the main motivational figures for the Dragonfly, and it's borrowed from the actually this is borrowed from the flattened butterfly paper. But it proves the point, shows the point that they made, is that if you compare the factory and the Dragonfly on equal terms, which means you have to reduce the bandwidth of the factory to a half bisection network, you get equal performance for the worst case, but the factory suffers greatly for uniform traffic. So the factory is more or less reliant on high full bisection bandwidth to be able to do uniform traffic in a decent way. Is the conclusion they draw from that figure. And obviously the Dragonfly for that cost is the preferred option, since you can route uniform traffic with much better performance. And I guess we're all quite in agreement on that. Neither uniform traffic nor worst case traffic are realistic, right? There's no such thing as an entirely uniform, nice traffic pattern, and no one in the right mind would create an application that requires worst case traffic patterns. Then you should try to redesign it, I think. So the reality is somewhere in between here. And I can't really tell you where it is, because it depends on the application, of course. Some will be better than others. But maybe we can try to find out at which level of this traffic badness you should go with one topology or the other. So to do this, we try to sort of get the upper and lower bound of the Dragonfly fixed in terms of the theoretical performance and bisection bandwidth. So I'll mostly talk about CBB ratio. CBB is, I think, constant bisection bandwidth. So the ratio is basically the ratio of traffic generated in the network divided by the bisection bandwidth. So that's the amount of bandwidth you get between two halves of the network when you divide it in two. So if you have a CBB ratio of 1, then you can basically push all the traffic to the other side without any contention if you have an ideal routing algorithm. If you have a CBB ratio of 2, then only half the traffic can cross the bisection without contention. So we spent some time on developing some equations for the bisection bandwidth for the Dragonfly. And then we generated a bunch of random traffic patterns and tried to place them on the topology using an LP solver to try to figure out how well we actually can place them. And this gives us some numbers and some equations we can do to do a final cost scalability analysis for the two topologies. So first, the fat tree. As I said, it's the most common topology for InfiniBand-based computers, supercomputers. It's easy to route. You can trivially deadlock-free if you go first up and down. You don't have to use any virtual channels or crazy logic to get it to work. Fault tolerance is also quite trivial. You can choose any upward path to get to your destination. So if any link fails, there exists alternative links. Doing it on the fly when you're inside the network is difficult, but you can always get around it. It has full bisection bandwidth. It's scalable for certain ranges with some notable hops. And it relies basically on static routing. That's the typical routing regime used on it. You can do static routing with multiple paths to do load balancing between the paths and stuff. Also, of course, you can do adaptivity if you want to by exploiting the number of different paths in the upward phase of the tree. Much of the cost of a topology is determined on how you build it. So for the study we've performed, we've assumed you would build them something like this. And of course it depends on the technology you're using, the size you're building, how much money you have, I guess. But we've constructed two sizes of factories with 3 tiers and with 4 tiers. And the idea here is to try to separate the optical link stage, because this is the expensive links that the Dragonfly tries to minimize, so we want to identify those. And inside the boxes, you can basically build small factories using just, what do you call them? Print boards, basically. So you just plug the switches into each other and you don't really have any cables at all internally. And then you use the cables to connect many such boxes to build the two different topologies. And then maybe have some electrical cables down to the processing nodes. But that's directly relative to the number of nodes you have, so it doesn't really affect the cost of the topologies when you compare them. The Dragonfly was not recently proposed anymore. I think it's 2009, so it's been around for 3 or 4 years. They proposed it as an alternative to the factory, as a cheaper alternative with similar performance. So it's a hierarchical topology. We have a global topology and we have a number of local topologies, and these are interconnected in some way. And they don't really specify what the global topology should be or the local topology should be, but they have some guidelines and suggestions. And that the basic is 3 parameters that defines the Dragonfly. And we'll go into that on the next slide. So it requires non-minimal global adaptive routing, which means that you have to use adaptive routing to be able to get any performance out of it at all. And most of the time you will have to also allow some kinds of non-minimal paths to be able to go around hotspots that will be created if you use just the minimal paths. And the standard implementation of the Dragonfly is it's quite sensitive. Is with a CBB 2 ratio. So it's blocking for the worst case traffic then. So this is the graphical representation of the Dragonfly. You have the intergroup topology in the big cloud up there, and then you have group topology, which is replicated lots of times around this huge cloud. And the group topology itself consists of a number of switches, and every switch is connected to a number of processors. So there's 3 parameters defining the topology. You have A, which is the number of switches in the group. So that's the 3 square boxes at the bottom. That's the A switches in the group. And each of these switches has P processors and H global links. And the global links are the links connecting the group to the other groups in the topology. So the intergroup topology is made up of the H links from the switches in the groups. And to keep this CBB ratio of 2, the authors of the original paper recommend you keep A twice as large as the number of P's and H's. And we'll see a bit more about that later. So how big can they be? So we'll just build a relatively small example. So if you have 16 port switches, given this requirement, how big can the Dragonfly be and how does it look? So 16 ports gives us 4 P's, 4 H's, and 8 A's, which translates to 7 links. Right, so A is 8, P is 4, H is 4. That gives us 8 switches, and these H switches constitute a group of these switches, and this group has 32 endpoints and 32 global links out to the remaining topology. And these 32 links then, each link connects to a different group. That gives us a bunch of groups, precisely 33. And all these are connected in one major global topology, which looks like more or less an all-to-all network. So that's a standard Dragonfly layout. So the next thing is, how do the groups look? Well, a group can be anything. You could put a factory in there, you could put a mesh in there, but obviously the authors of the paper like flattened butterflies, because that's what they wrote about earlier. So they recommend you put a one-dimensional flattened butterfly inside the group, which is basically an all-to-all network, similar to the global network, where every switch is connected to every other switch in the group, and every switch in the group is connected to a number of switches in the other groups. You can also, for scalability, you can also go up to a flattened butterfly with more dimensions, in which case you get more internal routing. You have to route in both dimensions. Maybe you have to do non-minimal routing in both dimensions, which gives you 4 hops inside a group just for the local communication. So it's perhaps not the best option, but it's there. So this is the 2-dimensional flattened butterfly implementation. So how do you route it? Well, obviously, if you have a source and destination, you would want to go directly from the source to the destination across the single link that's available. So there's one switch in the source group, that has a direct link to one switch in the destination group. And if your destination source is connected to these two switches, then you have a single hop to get to the other side of the topology, which is good. If it's not, then you have to do internal hops inside the group. And to get good performance, you have to spread the traffic, because if everyone in the source group wants to go to the destination group, you have to cross that single small link there. So usually you do some kind of a non-minimal routing. It's decided by the adaptive routing algorithm, so don't do a conscious decision, but you have to allow it. And then, depending on the traffic pattern, you also have to do internal routing inside all these switches. So in this case, we have non-minimal routing inside the group, source group, minimal routing inside the intermediate group, and non-minimal routing inside the destination group. It gives you 1, 2, 3, 4, 5, 6, 7, 8 different switches you have to pass through. In the worst case. So, let's look at the bisection bandwidth of this topology. I think the global bisection bandwidth is pretty easy. You take the amount of traffic that can be generated by a group, and you divide it by half the number of other groups in the network. Sorry, half the number of groups in the network that can receive traffic from this one. So you divide the network in two. All this traffic has to go to half the groups which are on the other side. That gives you this equation, which is, I think it's more or less the same that they presented in the original paper. And difficulty is more the local ratio. What's the CBB ratio of the groups, and does it really matter? So the model for the groups is the same as for the global topology. Take the amount of traffic you can generate in one switch and divide it by half the number of switches in the group, because you have direct links to all these switches. The difficulty is that the amount of traffic you have in the switch is dependent on how you do the global routing. And to be able to do anything rational with this, we need to know how much traffic do we expect to have in a group. So we've included a few variables. It's CS, CI, and C of D. So CS, C of S, basically tells you the fraction of flows that has to do internal routing in the source group. CI is the flows that do internal routing in the intermediate group, and CD are the flows that have to do internal routing in the destination group. And of course, this cannot be larger than 1 because you have a limited bandwidth on the link. And then you use this to modify the amount of traffic that comes in through the global link, which comes through the H's, and traffic generated by the terminals locally in the switch, which is represented by the P's. The n apostrophe squared root of A is to deal with multi-dimensional flattened butterflies. So we basically assume that the multi-dimensional flattened butterfly is symmetrical, so every dimension is equal sized, and then we can use this to calculate the size of a single dimension in the butterfly, which is where you put the bisection. So what's the useful value for the CS, CI, and CD? So the worst case is if you do internal routing in all the switches, in all the groups you pass through. So for the standard Dragonfly, this gives you the global CBB ratio of approximately 2. It depends on where you put the extra groups. So there's an odd number of groups in topology, so you can't really cut it in half the single groups. You have to put it on either side, so it's a bit uncertain there. And then everything is on the local one is basically 1, because that's the smallest value you can have, and you get the global and local CBB ratios of 2. Which is as expected, right? Next, we put this number of permutation patterns through an LP solver to try to place them in the topology. So we generated 10,000 permutations of pairs, and basically generated all possible paths with minimal and non-minimal routing, and tried to minimize the maximum load on every channel in the network. And then from results from this study, we saw how many of the placed paths, chosen paths, performed routing in the source, intermediate, and destination groups. So we came up with two numbers which are, or two different sets for two different types of traffic patterns, which more closely represent the actual load you would see in a group for any kind of traffic. So for random permutations, you have quite a lot of routing internally in the source group, obviously. You have quite a lot of routing in the destination group, but the intermediate group has not that much, because much of the traffic will be local, and there will not be much contention, so you can often choose a minimal path, which reduces your need for internal routing, because you don't get that amount of congestion. If you choose a more adversarial traffic pattern, like forcing all the traffic in one group to go to one other group, you get the situation that on the line 2 there, where the amount of routing internally in the source and the destination groups is reduced at the expense of increased routing in the intermediate group. The thing to note here is that some of these is always less than 2. So there's no flow that has to do non-minimal routing in all 3 groups, which is what we suggested as the worst case earlier, with all these values equal 1. So if we plug these numbers into the equation, we get the global blocking rate is still 2, it's unaltered, but the actual contention you get in the local group is reduced to 1.6, which is not too interesting in itself, but when you start to explore the different sizes of the topology and try to match them towards against the factory, for a certain CBB ratio, you're also interested in this. And the reason for this is that how do you create the bisection of the Dragonfly? You can do it across the global links, or you could just cut all the groups in half, which means that the CBB ratio of the entire topology will be the maximum of the local ratio and the global ratio. So in all these cases, the ratio is determined by the global link. But you can use this to increase the number of endpoints you can connect to a group at the expense of the group internal bisection bandwidth without affecting the overall bisection bandwidth, so you can make it more cost effective. Just a few figures from the permutations analysis. So at the top we have for the uniform traffic case, and it shows the distribution of load. So 70% of the channels have just a single traffic flow, and 30% of the channels, both local and global channels, have 2 flows. So for uniform traffic, there's a fair amount of blocking going on inside the tree. To the right, you have the path length distribution, which is just shows the average path length of all the flows in topology. If we go to the different group traffic pattern, then obviously the load on the global links is hugely increased, because all the traffic has to move out of the group and into another one. And we're pretty close to the worst case we can achieve in terms of blocking. And this is reflected in the path length distribution, where most of the paths are much longer to account for this. And just for the sake of it, I've read a lot of papers, well, some papers, and seen some discussions where people say you don't really need to care about non-minimal routing inside the groups in the Dragonfly. So, in this case, we did that. We excluded any path that used non-minimal routing, so we only permitted minimal routing inside the groups and non-minimal routing globally. And in that case, the load on the group channels increased beyond 2, which was sort of the theoretical foundation for the Dragonfly, up to 3. The reason for the increase in the global channels as well is because of the targets in the LP. You try to minimize the load on all the channels. So if you slacking on the local channels, you also slacken on the global channels, so they are allowed to increase as well. But it's impossible to keep the CBB ratio 2 inside the groups if you rely on minimal local routing. You have to use non-minimal there as well, at least for some parts. So, with that past us, we can concentrate on the comparison itself. So we've looked at 2 Dragonfly topologies and 2 factory topologies of sort of approximately comparable sizes. So the Dragonfly with a one-dimensional flattened butterfly in the group is roughly the same, spans roughly the same size interval as a 3-level factory, and the Dragonfly with a 2D flattened butterfly group corresponds more or less to a 4-level factory, although it can go far beyond as well. So we looked at the blocking ratio of these topologies and want to see how this behaves for different CBB ratios and for different sizes. And with one more thing. Anyway, for the equations we use for the CBB ratio, we then use the random permutation numbers, since these turn out to be identical to the worst case, the different group permutation numbers. And the worst case is, as we saw, quite unrealistic, so we haven't really bothered with that. And this also shows that the performance of the group doesn't really depend too much on the worst case performance doesn't really depend too much on the type of traffic you try to push through it. The amount of internal routing you get inside the groups in total remains more or less the same regardless of the traffic patterns. So the cost model is very simple. You have a number of switches. Every switch has a cost. You have a number of short links, which is the links connecting the processing node to the switches. We say they have an average of 2 meters and they have a cost per meter. And we have a number of long links with an average length and a meter cost. And the average length is calculated in the same way as it did in the Dragonfly paper, so based on the terminal density. There was a function to calculate the average length of the links on an installation. The costs are taken from a website, kernelsoftware.com. They had list prices for a bunch of different hardware. I think the largest one was 36 ports. The evaluation is done using 48 ports, so we've just assumed simplistically that in a short time the 48 port cost would be more or less the same as the 36 port cost, with the technology prices going downwards all the time, just to keep it simple. Short note on the sizes of the topologies. This is a bit relevant in the context of exascale computing. So for the 3 and 4, so for the 3-tier factory and the Dragonfly, the maximum size of the topologies for the different CBB ratios is low, very low. It's in the below 100,000. And going up in the CBB ratio, which is sort of backwards in the figure, it doesn't really improve that. For the 4-tier factory and the 2D flattened butterfly Dragonfly, can reach higher sizes, and this is one of the main points in favor of the Dragonfly. It's the huge, massive scalability it has for a given switch size compared to the factory. As I said, it's 48 port switches. If we were to change to 64 port switches, then the factory would cross 1 million cores. So if we increase the switch size, we're at the exascale for the factory as well. Which means they're both viable alternatives for an exascale system, given that you can solve all the other power problems. They can at least support the size. That's what we know for now. So, to generate these figures, we've generated this huge number of topologies. So basically, with a basic building block of 48 port switches, we just go brute force through all possible combinations you can use these ports in to build any topology that is conceivable, all the way from p equals 1 to p equals 46. We've also added the option of doing parallel links. So for the smaller topologies, you can reduce the number of switches and use parallel links to utilize all the ports to keep the scalability constant. And this is what you see, especially for the factory. The factory is actually a constant cost regardless of cost per endpoint, regardless of the size. So you have the size of the system on the x-axis, and you have cost per terminal on the y-axis. And this is for a CBB target of 1. So this is where the factory excels. This is where it's this is what it's made for. So the blue line at the bottom is the 3-tier factory. Obviously, it's the cheapest one. We know that the factories are made to be non-blocking. The 4-tier factory is also quite good. It's actually cheaper than the non-blocking Dragonfly, even the small one. So this is where the factories excel. This is Next, we get to the realm of the Dragonfly, CBB equals 2. This is the target the Dragonfly was designed for. And at this point, the Dragonfly for smaller topologies is now much cheaper than the factory, but for similar-sized large topologies, it's on par. It's not much above, it's not much below. If you increase up to the larger topology category, then the Dragonfly is the clear winner, with as much as $400 per terminal improvement. The problem, or the difficulty, is there's a lot of ways of building the different topologies. So for the factory, when you want to reduce the bisection bandwidth, you can do this only at the top, or you can do it at all levels. So if you do it only at the top, then you have full bisection bandwidth at the lower levels. So for the 3-tier factory, the top will be limited to half bisection, but the lower level of switches, lower level of links, will have full connectivity to support any kind of local traffic you want without contention. And that's the point where they have more or less the similar cost. If you choose now to slim all the way down, then you have CBB or half bisection all the way through your levels in the factory, which means it will perform worse in the for the local traffic, but the overall worst case isn't changed. So it's a much cheaper way of building a factory with the same poor performance, which is reflected by the figure on the right, where the factory is much cheaper again than the Dragonfly. And if you go back to the first figure I showed you, which was the motivation for the Dragonfly, where the factory had very bad uniform performance, this shows you can have the same bad uniform performance at an even lower price. It's no longer a equal cost comparison anymore. And the trend continues if you look at CBB 3. Now the Dragonfly has a clear advantage of the factory if you just slim the top, but if you slim everything, you still have a competitive edge. Sort of. I'll come back to this later on with some more refinements, if you think it's a bit unrealistic that I try to sell the factory in this way. Right, so these are two other metrics that people often think are important to describe a topology. That's the number of cables you have to use to connect the number of terminals on the left side, cables per terminal, and the number of terminals you can connect to every switch. So you want the number of cables per terminals to be low, and you want the number of terminals you can connect to each switch to be high. And obviously this mirrors the cost in the previous figures, where the factory is very good at building non-blocking topologies, and the Dragonfly is quite expensive for the non-blocking topology. But what you can use this for on the next slide is to figure out what makes the Dragonfly cheaper. So the reduction in cables per terminals when we go to CBB2 for the Dragonfly, that's this one, is larger than the reduction in cost, which means that going from CBB1 to CBB2 for the Dragonfly has a larger impact on the short links than on the long links, which is interesting since it's the long links they want to optimize on. And it also shows why the CBB ratio of the group itself is important in such a study. Otherwise, you can just bring it all the way down without affecting the ratio at all. On the right, you have, if you slim everything again, obviously that makes it cheaper, so it's not that interesting. Same thing for the terminals per switches. The Dragonfly has a better is better able to exploit the reduction in ratio in terms of terminals per switch. Yeah. So let's try to summarize. So the factory is obviously the best topology for worst case traffic, and the Dragonfly is obviously the best topology for uniform traffic. Because if you look at the, if you compare with the full bisection fat tree, then these figures would sort of be reversed. The performance for the uniform traffic would be identical, but for the worst case, the Dragonfly would be at 50% and the factory would be at 100%. So it's the opposite of that one. So perhaps comparing the Dragonfly and factories for the same CBB ratios is not entirely the best comparison. So where do they cross? So you can't really compare a CBB2 factory and a CBB2 Dragonfly with a CBB. You can't compare a CBB2 Dragonfly and a CBB2 factory, or a CBB1 Dragonfly and a CBB factory, because they're designed for completely different things, they perform differently, and they have quite different costs. So perhaps the fair comparison is the factory, regular factory as it's always been designed, with the Dragonfly as it always has been designed. And this is what we're trying to do here. So the whatever color this is, the square boxes is the cost per terminal for a factory. It's quite stable at around $2,000 per terminal. And then for the remaining lines here, we have CBB2, 1.7, 1.5, 1.4, 1.2, and 1. So this, with this figure, we try to figure out what's the crossing point? How bad does the traffic have to be before you should choose the fat tree above the Dragonfly? And it turns out it's at around CBB equals 1.5. And at CBB 1.5, you can have 75% of your traffic crossing the bisection without any contention if you have a good routing algorithm. That appears to be sort of the crossing point. So what does this mean in terms of traffic patterns? Honestly, I'm not entirely sure. But what I know is that lots of these MPI patterns go in, for instance, MPI all-to-all has a bunch of stages, and each stage contains one permutation of communication. And you can do this in a bad way or in a good way. And doing it a good way means you have to synchronize who talks to whom in which time slot, and it's quite complex. And if you do it in a bad way, you have to have a non-blocking network for full performance. So, yeah, who knows? But what I noticed also, in most of the papers, the best performance I could see for the Dragonfly was around 70% for uniform traffic. 70% utilization of the network. And this is probably because you have to rely on adaptive routing algorithms. Adaptivity is difficult. It's a young topology. People haven't had time to tune the adaptive algorithms. You have to make local decisions based on the blocking of the global links to be able to have best performance. While the factory is well studied, so you can well understood. So most of the papers I see on that do a factory evaluation is able to achieve around 90% throughput for uniform traffic. So that means that there's extra cost of the Dragonfly in terms of performance. So if you include the performance in the cost per terminal, so it means you get cost per terminal per performance or per throughput. You the difference between them is actually reduced. So that means you scale the cost per terminal with the efficiency of the factory. So you divide it by 0.9, it becomes more expensive. And you do the same for the Dragonfly, divided by 0.7. And perhaps that is a more fair comparison of the Dragonfly and factory. They're closer. They now perform, for uniform traffic, they would perform equally for that given cost. The factory would be better for worse traffic, and perhaps that makes up for the increased cost. Who knows? That's not really what I'm here to decide. And we can bring this to its full crazy conclusion. If we do the same scaling for all the different CBB ratios for the Dragonfly, we see that the traffic doesn't really have to be very bad before it is more cost efficient to use the factory for the amount of performance you get out of the topology. On the other hand, if you have uniform traffic, then there's no question, and I don't really have to say anything more. So, yeah. It's difficult to compare topology, so I think that's one of my big conclusions after doing this. There's a huge amount of factors that you have to look into, and if you want to compare them on their own without having to deal with routing implementation complexities that affect performance, you really have to try to look at the theoretical foundation of the topology, not only the what you can measure in a simulation. And yeah, well, there's no clear conclusion. The factory works for worst case traffic, and the Dragonfly works for uniform traffic. And I hope I've sort of tried to illustrate that there is a point where you cross, and whether you want to choose the one or the other, it depends on the traffic pattern you actually know your application has. It's the same as for the torus, right? If you know you have very neighbor-intensive traffic, you choose a torus or a mesh. If you have very bad traffic, you choose a factory. If you have very benign traffic, you choose a Dragonfly, or maybe you think about the factory if you're not entirely sure. And a final caveat, of course, is that the Dragonfly is complex. You have adaptive routing, you have lots of virtual channels to keep it deadlock-free, and so on. So it's more expensive to deal with, even though it's cheaper to build. And I'll stop now.